Well, you may or may not like this cartoon showing the deadly sins of statistics. Someone didn't randomize. They accepted the alternative instead of failed to reject and extrapolated, which goes back to linear regression. All right, so today we're talking about tests involving paired differences. Let's say we're looking at a new diet plan to help people lose weight. The table at right shows the weight before the program and after. Do you believe most people lost weight, or on average, did people lose weight? So, how much weight should someone expect to lose with 95% confidence? And that's what we're going to be looking at in this lesson: is how do we determine if yes, there actually is a difference, and then also determine how much a difference could be. Now, first of all, since I'm saying differences, it makes sense to subtract the weights. But we wouldn't want to subtract the weight for subject A from subject F because those don't go together. If there's a good reason to pair one data point in one sample with the data point in the other sample, then we can say the samples are paired or dependent. So this 340 goes with the 328. It doesn't go with the 158. Which makes sense. This is a person and they're on the diet before and after. So types of data which may be paired include before and after, studies from the same individuals, studies of closely matched individuals like twins. And in fact, I have some twins in my AP class and they say, yeah, they get asked to do studies all the time. To test paired data, you must first calculate the differences in the measurement. And how can we do that easily? Well, getting a list of differences on the TI-84. First of all, we're going to put the initial two list in the list of stats, this thing over here. So I'm going to do that by pressing stats and then selecting edit. Enter both lists of the data in the calculator. In this case, I did L1 and L2. Enter the list for your differences by going to a new list, L3, and here I scrolled up all the way to the top so that this is highlighted right here. And that shows L3 equals. Then to get this L1, I press second distribution, which pulls up the list name, and select your first list that you're subtracting from. Then press minus, and then press second distribution again, and then pick your second list. In this case, it's list 2. It can be whichever two lists you want to work with. Then you press enter, and what's going to happen is this column that was empty is going to fill up with all the differences. Now you can switch the before and after. I could have done L2 minus L1, and all that will do is switch the sign. So this positive 12 would become negative 12, positive 6 becomes negative 6, the negative 4 becomes positive 4, and you get the idea. Creating hypothesis will be a little bit different now because we're looking at the difference of the before and the after, or the matched pair, basically. So it's going to be in the form H naught, which is our null. The mean of the difference equals 0, or mu of D is the mean of the differences. Now, your alternate hypotheses, just as before, can take one of three forms. It can be left-tailed, so that means the mean is less than 0. It can be right-tailed, so the mean is greater than 0. Or it can be two-tailed, which means the mean is not equal to 0. We still have conditions. You're not going to have to do a lot with this, but I'm going to state them anyways. The large normal, where n is greater than or equal to 30 for the set of pairs, and the population is approximately normal. And when we say approximately normal, we mean very approximate. Our differences, the histogram of the differences just needs to be mound-shaped and symmetric. If we have any outliers, that will mess us up. If there's any skew, that will mess us up. Random. The data must come from a well-designed random sample or a randomized experiment. Note that being representative is the goal of this condition. So if I tell you it's representative, you don't have to worry about it. And then paired data. There has to be a reason to match one data point in one set or sample with the data point in another set. So let's go ahead and look at our weight loss example. And I went ahead and created a histogram of the differences. So our hypothesis is that the difference is 0, where the difference is before minus after. It really helps to state this because sometimes people subtract in a different direction. And just as long as you make sure that your alternate hypothesis makes sense for your direction, it's okay. So if I'm going before minus after, Do I expect them to weigh more or less after the new diet? Ideally, it should be less. So I should have a positive difference. So my differences should be greater than 0. Now, if I had said after minus before, and I'm allowed to do that, then I would say the difference has to be less than 0 for the alternative hypothesis. Now, looking at the histogram, you can see it is mound-shaped and symmetrical, so that large normal condition is met. I'm not sure if we met the random condition. It didn't really say when I was making up my problem. I should have said something. Where maybe our sample is representative, and I'll tell you, well, let's assume it's representative. But the data is definitely paired, and that's the other condition we have. So calculating the test statistic by hand, if we use D bar as the mean of the differences in our sample, that would go right there. So it's kind of like the old X bar. By the way, on the calculator, it's still normally X bar. The hypothesized value is the mean of the differences. By the way, this is almost always 0, so this part might go away. And then we have this S of D, which is the standard error for the sample, and N is the number of pairs. So calculating the test statistic and p-value with the TI-84, the good news, it will do a lot of this automatically. And here's how we do it. We press stats and scroll to test, just like we've been doing. We're going to select 2, which is a t-test. And you're probably going, wait a second, haven't we already used that one before? Yes, we have, for finding the average of a sample. In this case, we're going to be finding the average of the differences, or testing the average, really. Our input, in this case, we're dealing with data, and our mu naught is the hypothesized value. And by the way, this is almost always 0. So that should almost always be 0 there. You might want to make a note. I probably could have added that in. The list, be sure to select the list that has the differences of the data. Don't pick the before, don't pick the after, pick the subtracted list. For frequency, it's almost always 1 unless you have a second list of frequencies, maybe an L4, wherever it is. And mu, select the form that matches your alternative or alternate hypothesis. Then after you hit calculate, we're going to get the output, all right? And the output screen, the first line is your alternate hypothesis right there. Second one is your test statistic T, then your p-value, your sample mean, the standard error for your sample. Now, if you're using stats instead of data, like here, then you also need to provide the mean, X bar, or D bar if you want. Notice how it says X bar there. And you'll need to provide the standard deviation for the sample, or standard error, depending how you word it. And then the sample size, N, which is 10. And you're still doing the alternate hypothesis the same way we did before. Pick the one that matches your alternate, and then you hit calculate, and you'll get a very similar response right there. So compare p-value to the significance level to come to a conclusion. We're going to, if the p-value is less than our alpha, alpha is our significance level, then we reject H0. And we say we have convincing evidence for the alternative hypothesis. If it's greater, we fail to reject. And we say we don't have enough evidence. We have insufficient evidence. So based on our weight loss example, we had a t-value of 4.16 and a p-value of 0.0012. Typical alpha is 0.05. That's definitely less than your typical alpha, all right? So we're going to reject H0, that there is no difference in weight. So that's the null, that there is no difference. We're going to say we have convincing evidence for the alternative, that the weight loss is greater than 0. So we can also come up for the confidence interval for the differences, saying, oh, how much did people lose on average on this? Or what can we expect? Well, if we press stat and scroll to test, and we're going to scroll now to 8, which is t interval. So we've used that before, and we get to use it again. So it's the same interval you did before. For your input, in this case, I'm going to go ahead and put stats. And then X bar is your mean from the sample. S of X is the standard error or deviation from the sample. N is the sample size. C is the confidence level in decimal form. So you wouldn't put 95, you put 0.95. And then your output right here, this is your lower limit and this is your upper limit. You already had these three, so there's no need for me to describe them again. Now you can also use a list of data, and to do it that way, you press Stat, Test, same thing, select 8T interval. For input, select Data and press Enter. And then you're going to select List 3 probably. Keep track of where you put those differences. And remember, it is the list of the differences. It's not the before, it's not the after. Make sure your frequency is 1 unless you have frequency, say, in list some other list. And the confidence level is still the same. It's in the decimal form. So based on the output I had from the previous screen, what would be a confidence level or interval, that should say interval, for the amount of weight loss in the new program? Well, our interval was 3.7415 to 12.658. We are 95% confident that participants lost between 3.74 and 12.66 pounds on the new diet.